cotangent function and look at its derivative. So if I have a cotangent function, let's say t.
Isn't it negative?
So this is equal to 1 over tangent t, or in a more frequently term, it's going to be equal to cosine t over sine t. All right? So that's our definition of cosine t. Right? And if I want to compute cotangent prime t, so the derivative of a cotangent function, I can use the quotient rule for taking derivatives. All right? So let's just work out what the cosine t derivative is.
Sine squared.
So it's going to be sine squared t in the denominator.
Negative
sine t
times
sine t
minus or plus. Yeah.
minus cosine t is the derivative of the denominator
Times
and cosine t. So I have a sine squared minus cosine squared is going to be minus sine squared t plus cosine squared t divided by sine squared t. Every time we see sine squared plus cosine squared, we're extremely happy. So it's going to be minus 1 over sine squared t. Okay? So the trigonometric functions, you have sine, cosine, tangent, and also their reciprocals. Basically, all the trigonometric functions will be derived from cosine and sine. As long as you remember how to do derivative for cosine and sine. And you remember the only trigonometric identity we use pretty much everywhere, sine squared plus cosine squared is equal to 1. You can deal with all the trigonometric functions. Okay, so this is cotangent prime, which is equal to minus 1 over sine squared t. So using this formula, I'll be able to do the computation right here. So Amanda, walk with me. It's going to be.
So those are all constants.
Mm-hmm.
Keep all of them.
2
Z to the
z to 4
times negative 1 over sine t.
negative 1 over sine. What is inside is x z squared, all right?
What was that?
So I have to take the derivative of this function with respect to x. Yes?
Okay. Yeah.
So I have to take the derivative for cotangent t first, which is exactly what we have right here. Right? So it's going to be minus sine squared xz, and then change rules that I have to take the derivative of xz with respect to x. So what do you got?
Z.
Just z. So in the end, we have a minus 2z to 5 divided by sine square xz. Now with me? Agree? Any questions? Okay, still I want to do partial s, partial z. Okay, now x is the constant. Z becomes the only independent variable.
We have a chain rule there. So it'd be 8z to the third.
So tell me first what rule you want to use if I'm taking derivative with respect to z.
Oh, it's a product rule.
Product rule. So it's going to be z to 4 times another function involving z.
Yeah.
Right? So I did take derivative of this guy first. You are getting 8z to
third.
3. So cotangent x z. And then
Plus.
plus 2.
Oh, 2z to the fourth
Mm-hmm.
times.
And the derivative of this guy, right?
Yeah.
So it's going to be
Negative
negative
1 over sine t.
1 sine squared x
Oh, yeah.
z, all right? And then derivative of the inside with respect to z, you're getting a
Oh,
x, okay? So in the end, it's going to be 8z to 3 cotangent xz minus 2xz to 4 divided by sine squared xz. Okay, so that's our partial derivative. Practice the last week. So I have, I will keep monitoring your performance on the my math lab. Okay, so let's say you have a question? What is the question?
For the test,
Mm-hmm.
would you want us to put it under sine squared t, or can we put it cosecant?
Well, it doesn't matter. You can use for cosecant or sine. Right. That's not a main issue here. Okay. So in today's lecture, I want to talk about section 13.5, chain rule and implicit differentiation. Okay. So chain rule and implicit differentiation are very, very applicable calculus skills you can use. First, I want to recall briefly what chain rule is coming from the single variable calculus. So the single variable calculus, we're using chain rule pretty much everywhere, right? Sometimes you didn't even realize you're using the chain rule. For instance, here, if I'm taking derivative with respect to x, first I'm taking derivative of cotangent, and then I'm looking at an inside function as a polynomial. So I'm taking the inside derivative again. So you're using chain rule implicitly here already. So to extract what we did, we have a function y is equal to f of x, and x is equal to a new function g of a new independent variable u. Okay? And then I can take the derivative dy with respect to du linked by this x as the intermediate variable here. So I'm taking the derivative with respect to x, and then a derivative with respect to t. Right? So it's dy dx times dx du. Okay? So this is the chain rule in single variable calculus. Or if you want to write down this f and g, this is going to be f prime evaluated at gu multiplied by g prime evaluated at u. Okay? So you have this chain of dependence here. So the dependent variable is going to be y. First, it is depending on x, and then it is depending on u. So that's why it's called a chain rule. You have a chain of dependence relations between y, x, and u. By eliminating the variable x, you can get a dependence relation between y and u. So that's why we can get a dy over du right here. Okay? So this chain rule will also happen for multivariable calculus, which I will give you a very simple graph here. So if I have a function y z is equal to f, x, and y. Okay? So I have two independent variables here, x and y. And both of them will be variables depending on some new variables. So x will be equal to x, u, and v. And y will be equal to a function involving two new variables, u and v as well. So in the graph, you can see we have a dependent variable in the very beginning. It is depending on xy, and xy are depending on u and v. So you have also got this chain of dependence here. Okay? So by eliminating the intermediate variable x and y, I will get a dependence relation between z and u and v. So we can ask the partial derivative of z with respect to new variables u and v. Okay? So that is the chain rule we can talk about. But because in multivariable case, there are all kinds of number of variables here, so the varieties are more than the single variable calculus. I do want to mention one motivation of considering chain rule in calculus. So calculus is about a rate of change. So it is studying the change relation between different variables. So for example, if I'm liking Z as the stock market, right? What stock market are there in the States? NASDAQ, I think. And what's the other major?
Dow.
Dow, yeah. And then you have all major companies as the components of the stock market. You have PayPal, you have some oil company, everything. And the performance of each stock is depending on different variables as well. In fact, the dependence relation for the stock market is much more complicated than the simple layer chain, right? For instance, if you're looking at the companies all using Apple product, so if Apple is changing, all the other companies are also changing. But the relations are not as simple as this layer chain rule. But the bottom line is, when you study the rate of change, how the weather of California is changing ultimately into the stock market, it is a chain of change, all right? So the weather in California is gonna change the farming probably, and then it's gonna change the transportation and so on. So in the end, you're getting some symptoms of the change of the stock market. So this rule of computing the rate of change for multivariable calculus is very applicable in daily life. So I want to look at the simplest case to begin from. So here I have this rule of dependence. I have independent variable x and y, and dependent variable z here. Okay. So when I introduce my new variable, I only have one new variable t. So both x and y are depending on one single variable t. Okay. So this is pretty much the easiest possible chain rule here. So I have z as my dependent variable. These x and y are two intermediate variables. So if I eliminate x and y, I'm getting a function of z with respect to t. Okay? So if you eliminate x and y as the two intermediate variables, you're getting a single variable function. Okay? So I can compute the derivative of z with respect to t. Okay? So here, so if z is equal to f, x, and y, x is a variable of t, y is a variable of t as well. So I have the chain rule dz over dt is equal to partial f z partial x dx dt plus partial z partial y dy dt. Okay, so this is the first chain rule I want to introduce. Okay, so this is in the simplest form. As we already agreed, if we eliminate x and y, we're getting a function of z with respect to one single variable t. Okay, and the chain rule says the derivative of z with respect to t is equal to partial z partial x, which is going into this intermediate variable, and then dx over dt. And then you can go over the other intermediate variable y here, so you're getting partial z partial y multiplied by dy dt. I want to mention this chain rule in the very beginning for the other very important reason. I want to distinguish the relation and difference between partial and d. Okay, so we're using these two terminologies and notations all the time. Okay, and they are all contained in this simple equation. Both of them are appearing here. Okay, what is the difference between these two notations? Where do we want to use this partial sign? Where do we want to use this differential sign d here? If you look at this equation, why I'm using d here and I'm using a partial for this variable? Reckon a guess? It's not that significant, actually. The difference between them is not that significant. Both of them are talking about rate of change. Both of them are talking about differentials. One is the differential. The other one is a partial differential. The partial differential is used if you have two variables in the dependence. Are you with me? Mm-hmm. So I'm using partial z partial x because when I define z with respect to x, z cannot be completely determined by x. I have to use the other variable y as well. Am I right? So you cannot use x to completely determine z. So that's why you have a partial relation here. Okay? However, if I'm looking at the relation between x and t, x will be completely determined by t. Am I right? So this is just a regular differentiation. There's no partial right here. Are you with me? Similarly, here, if I'm looking at the relation between z and y, the dependence relation, then z cannot be completely determined by y. I have to have the other variable x. Okay? That's why I'm using a partial sign right here. And y is completely determined by t, so that's why I'm using a d right here. And when you combine them together, z will be completely determined by t if you eliminate x and y. That's why we're getting a d right here. Okay? So partial differentiation only is used if you have a partial dependence. Okay, d is here if the function is just a function with one single variable. Their difference is not that significant. It's just terminology and notation. You want to use it correctly. Okay, so I want to practice this principle, this chain rule, by looking at one example. So let's say I have a z is equal to 2x cosine 1. X is equal to t to 5. Y is equal to 2t to 4. So I want to compute dz over dt. So who I want to look for? Jonathan. Is Jonathan here? Okay, so I'll work with you. So first, I want just to write down that point length. It's going to be partial z, partial x, dx dt plus partial z, partial y, dy dt. Okay? So chain rule, in order to apply this chain rule, it's just a matter of computing the partial derivatives and the regular derivatives. Okay? So let's practice our partial derivatives too. Partial z, partial x, what do we got?
It's all going to be a constant, right?
Y is constant, and x is still the variable, right?
Okay. So just 2 cosine y.
Cosine y multiplied by dx dt.